So in history, we say right now you can see the first antennas that we have seen for our television in around 1990s or 1980s to connect televisions is Yagut antenna, which has a folded dipole, a radiator, electromagnetic waves, and it has a bunch of other long cables which act as reflector and directors to get the energy in a certain direction. Then shortly after that, in 1930s, horn antennas were developed. The horn antennas, which is the right next to the Jaeger antenna, this were more efficient antennas which could provide which would provide links to certain more distance. Then after that, dish antennas were developed in 1960s. As you can see, that's pretty common still. Now we use it for our direct-to-home television networks. It's probably everywhere. Apart from DTH, these dish antennas are also used to communicate to satellites and for deep space explorations. Then in 1970s, a very interesting thing happened. Now this antenna actually brought about an evolution because this antenna was crucial in joining printed circuits or rather printed circuit boards along with an antenna. So we were able to get an antenna which was a 2D, a planar antenna. If you pay attention, before this, these antennas, horn antennas, jagged antennas, all were 3D structures and they were pretty big. But now with the introduction of microstrip antennas, we are able to integrate microstrip antennas, or these radiators with RF read lines or any kind of structures. Now, see at the bottom left, the blue ones, these are a picture of microstrip antennas. They are used in a group of elements, and this is probably the back of a satellite. So they were used pretty much everywhere. Then in 1980s, another antenna came into picture that was planar inverted F antennas. Now, why these are important? Modern communication, where we use mobile phones or any other communicating devices, they were pretty big in 1980s, 1990s when they were introduced first, and they were not very compact or easy to handle. So for development of that, this planar inverted F antennas are very important because these antennas could be used in printed form as well as these antennas could be smaller. So that means since the antennas, the communicating structure is small, our device could be small. So these are the basic history of how antennas evolved, and of course, after 1980s, many more different types of antennas were developed and are still developing for different applications. Let's look at some of the present scenarios. I found these things interesting. Some of them are like, if we go to the extreme left, we see an image of Marco CubeSat. Now, this Marco CubeSat is a satellite which was used to communicate with Mars satellite from Earth, or rather, it's, they're in the Mars. It's a kind of, if you can see, there are wheels attached to the satellite, and these are kind of rovers kind of thing. Solar panels, and there is next to a bunch of patches, copper printed over some kind of substrate. So this is a kind of antenna known as reflector array. So this is used in, or rather, this is a more. Then, if we go at the bottom left, we see the picture of a antenna that is pretty common in any airports. Wherever, if we try to look through the airports, we'll definitely see at least, even if it's also visible from flight, at least while taking off or landing, you will see this kind of antennas pretty much there in all the airports. And then after that, next to it, you can see some few soldiers standing next to some kind of a dish antenna. Now, these antennas are important for defense sector, where they try to communicate with either a satellite or within themselves. And of course, it's pretty common, everyone uses it, we cannot live without it. Fortunately or unfortunately, these are smartphone antennas. And you can see these antennas have a bunch of different types. Like if you look at the cell phone, at the top, the blue colored, the first one on the left, you can see the LTE MIMO antennas, which is pretty important. MIMOs are important for giving us good clarity and good throughput. Then you can see GPS antennas. Now all the phones have GPS, so that we can track ourselves, and of course we can secretly track other people if you want. Then we also have some other, okay, if you look at the antenna, you will have MIMO antenna horizontal as well as vertical polarization. Now, because we do not use antenna always in the same orientation, right? We use antenna in different orientation, like it could be horizontal, it could be vertical. So depending on that, they have both types of antenna, so that at least one of them is connected. Now, after that, we have Wi-Fi transmit and receive antennas. Nowadays, that's again another important feature of smartphones where you need to connect the internet through Wi-Fi. Next one is again Bluetooth. I think it's kind of obsolete nowadays, but again, we do use Bluetooth headsets and headphones or some other smartwatches, some other devices. So probably that's still required in a smartwatch, smart antenna, a smart mobile phone, sorry. And after that, we do have PCS or CDMA antenna. That is the main antenna which communicates with your SIM call provider or SIM provider, right? So as you can see, there are different types of antennas that are present in present scenarios, which are used everywhere from space to day-to-day communication as well as defense. Let me briefly go through some of the works we did in AML SDHCU, what we contributed to the present present research. I would mainly focus on what I have worked, and also I will try to explain how we design an antenna from a scratch, like from a specification. Like I will mostly talk about my US Navy project where we try to establish a troposcatter communication. I will explain that in detail, what's troposcatter, what is that, and other things. But before that, let me just give you a quick review what we have worked on last couple of years in our lab. AML is basically Antenna Microwave Laboratory. So as this slide you can see on the left, there is a troposphere and a naval ship in the ocean, and there's another antenna at the ground station which are connecting to each other through a non-line of sight. Non-line of sight, that means they are not directly in line of sight. They're communicating through a troposcatter link. So for that, an antenna was developed on the left. Then on the right, there are similar version was developed at Ka band for millimeter wave technology, and the related circuitry and antenna is presented here. Now, this one is another interesting thing. These are lens, which are at much more higher frequencies. Like at top left, the antenna that you see can be used for ADS. ADS is your autonomous driver assistance system that is pretty famous in cars nowadays, where we like want the car to drive in front instead of us. That is, we basically want to get rid of all the drivers. Cars should drive. So yeah, so that's in V band. Then some of the 3D printed structures to the extreme right top for CP. Then we have a very wideband lens-based antenna structure, Vivaldi antenna on the left bottom, which would cover all the bands. Like if we talk about, we have ultra-wideband from 3 to 11 gigahertz, which covers Wi-Fi, Bluetooth, many other medical frequencies. Then after that, it also covers some satellite ranges, etc. Then on the extreme right bottom, you can see some of the 3D printed structures that we develop in our lab for different purposes. Yeah, okay. Okay, so like I was saying, I will try to give a brief preview of how we start an antenna from scratch. How does an antenna engineer think about solving a problem, and how we deliver an end product. I hope that will be useful. So the main purpose of my work was to develop a troposcatter communication, which was sponsored by Office of Naval Research from US. Now, before knowing that, we have to understand what is a troposcatter. Now, troposphere is the layer of atmosphere where the air density gradually decreases as we go higher. And if we try to remember our physics background or physics basics, do we understand or we can remember the term total internal reflection, where if a light ray moves from higher refractive index to lower refractive index at an angle more than critical angle, it gets reflected back. So essentially, here in troposcatter communication, we try to utilize that phenomenon. Now, of course, unlike what we have studied in our physics classes, that we have a glass and then we try to send light ray through it and get it total internal reflection. That's not going to happen in troposphere. Troposphere, the air density gradually decreases. So refractive index gradually decreases from bottom to top. So this is going to be a more gradual total internal reflection. Now another thing we have to consider here was that troposphere is always changing, or rather the atmosphere is always changing. It depends, the refractive index or density of air depends on a lot of things. Let's say we have a cloudy weather today. So if we have a cloudy weather, the air density is going to be different. We have a very, we have summer, we have winter, different seasons. Depending on that, the refractive index of the air is going to be different. So all those factors affect how we gonna look at this troposcatter link, or how we're going to use this troposcatter link. Now, the other thing is why it is important. Now, why is defense interested in troposcatter? Are they stupid? We have satellite communication. Why we should go back and look at like point-to-point communication, where we just have one another? But we have to think about it that from a defense point of view, the first thing that comes to mind is security. We want that our communication links are not intercepted by enemies. So from that point, I will say that once the attack being used by different users, it's very easy to intercept. Other people can intercept those signals. So that's where we said compared to satellite communication, it is more resilient in denied, disrupted, intermittent, and limited bandwidth condition. This is actually a so-called Navy term, where they do not use the term like what should I say, that jamming. In normal layman's term, they do not use the term jamming. Jamming is prohibited. You cannot say jamming. You cannot say jamming. If you say jamming, you will be immediately caught by the USA. No, USA. Okay, so that was the advantage. And this troposcatter can be used till 300 kilometer and from 10 megahertz to 10 gigahertz range. Now, coming back to the communication links, what's the challenge? Like I mentioned, atmosphere is very fragile, and depending on temperature, depending on atmospheric conditions, weather, season, this common scatter volume that you see in the picture, that changes, location changes. So it is pretty essential that before establishing a communication, we need to know the exact position where this common scatter volume, where they are getting total internal reflection, is detected, or is like tracked rather. Also, the other application is like, now if you're trying to develop it for Navy or naval vessels, like some ships, they are not going to sit stagnant in water. They're going to move, right? So when they are going to move, even the links will be different. So even for the tracking has to be developed, which will track this scatter volume before establishing a link. And once we establish the link, we will be able to keep a track where the optimum scatter volume is. So that was the problem that we were dealing with. Now, let us look at some of the antennas that are state of art, which are already used in Navy. Some of them you can see they are, the links are all provided, you can check online. And most of them are similar to what we see in our daily homes or daily houses, but slightly bigger. Of course, you can see they are much bigger than the soldiers. And I will tell you, the soldiers are pretty tall. They are mostly 2-meter tall people. And you can see that the reflectors are almost twice their size. So they are probably 3 to 4 meter reflectors, most of them. Of course, so if you look at the problem is most of them are fixed beam designs. Now, what's a fixed beam? Fixed beam design, that means my antenna, the energy in which The energy of the antenna is directed only in one direction. We are not able to move it without moving the antenna. So that's called a fixed beam. Then if it is fixed beam, now before that, if you remember that in the previous slide, we talked about how we need to track. Now, if I'm going to track, of course, I have to move my antenna. Like you cannot, like physically, let's say, if I'm tracking visual person is moving, right? So similarly, you have to move the reflector. It's like moving that. Now that's a problem. Why? Then so many things are moving, and these reflectors are so large, 4 meter. It consumes a lot of energy. So depending on the state of art, we needed to find a solution. So first thing that an engineer do is go through some of the specifications that are given here. Try my best to explain what all these parameters mean and why we set the kind of values. First of all is now are we able to translate in a particular direction compared to other direction? Like, of course, if you're, let's say again, coming to the same example, if I'm looking at a person who is moving, I want my complete attention towards that person, right? I do not want to see all around. And if you are trying to focus something, we cannot see the surroundings. More likely we are looking at that person. So that in that respect, antenna gain helps a lot, and definitely higher the number, better it is, because the atmosphere has certain losses. I'm pretty sure we sometimes complain that our signals are weak, our Wi-Fi is weak. Now, why is that? Because we are far away from the source. Since we are far away from the source, the energy is dying out, right? So most of these factors actually determine what kind of value it should be. And it is the unit of gain is actually dBi. The reason for that is we try to compare the gain in terms of an isotropic antenna, isotropic source, which generally radiates energy in all directions. Okay. So first was antenna gain, then is beam steering. Okay. So there's the elephant in the room, beam steering, plus minus 25 degrees. Now what's beam steering is, let's again come back to the same example. I'm moving my head. Let's say I'm limited. I cannot move my head till after 25 degrees. I cannot look back. So that's kind of thing I will say beam steering is. Now, physical dimension. Now, if you go back to the previous slides, you can see that the antennas were pretty big. They were almost twice the size of human being. That means another thing. In case of emergency, it's not easy to take them, right? It's not easy to assemble them as neatly, which we want for our defense people to do that. So physical dimension was lesson 2. And then for tracking, yeah, we want to track where the optimum scatter volume is. So monopulse tracking was used. Now for monopulse tracking, a feature is we need to develop a sum and a null pattern. Okay, I will talk more about that while going through the antenna structures. Then, of course, a more simpler mechanical rotation. Now, what is that? Why I'm saying simpler mechanical rotation? Now, if you if you connect the last time, what I was saying is that I'm trying to move my head. Won't it be good if I don't move my head and I just move my eyeballs and I'm still able to track the object or track the person? So it's like that. Okay, I'm not being obvious, I'm not moving, less energy consumed, I'm just moving my eyeballs and tracking the person. So that is what we are trying to do. We are trying to do, we're still trying to do mechanical rotation, but we are trying to do it without moving my head. Now, of course, there are other examples like I'm sure if you go through which some of the base station antennas you see at the TV do that. They do steer the beam electronically. Actually, it's like moving the head electronically. That means they are neither moving the head, they're neither moving the eyeballs, but they still can look at different direction. Now, coming back, we are still doing mechanical rotation, means we are still doing some kind of movement. Now we need lighter moving parts. So instead of, like I said, instead of moving the head, we're just moving the eyeballs. So the moving part are lighter now. Okay, so coming back now, where the requirements were that we need to track. We selected a certain kind of tracking system that was monopulse tracking. So what monopulse required was a sum beam and a null. Then we needed to somehow able to do beam steering, that is able to move the beam in certain direction. And we need to have a certain gain and magnitude requirement. So we first concluded, let's look at monopulse tracking and what is meant by sum and difference beam. From the extreme left, at the bottom, the orange figure, that's actually a simulated model of the antenna. It is called triple mode horn antenna. It generates the pattern. Triple mode, of course, that means it has three types of modes that it can operate on. As you can see from the three different patterns, they are named as TE11, TM01, and TE21. And at the extreme left top, you can see the horn that has been developed using 3D printing. So now let me discuss what is sum and what is difference. By sum, what we mean is a pattern which is similar to the T11 mode, the first top mode, where we have our energy. Okay, let me also tell you, red means more energy, and as we go down towards the blue, the energy gets reduced. Okay. So as you can see the first figure, T11 mode, the red energy is more concentrated along the intended direction, which is the Z or Z direction, right? And then the next two, TM01 and T21, these are different modes. That means at the intended direction, we have as least energy as possible. Now, I will not go in details about what is monopulse tracking or nitty-gritty details of that, but I would say that using this both sum, they call it sum, where you have the peak energy in a certain direction. Using certain signal processing algorithms, we are able to track location, or we are able to see where the object is moving from this pattern. Now, as an antenna engineer, two things are important. Okay, so let me again, I think I should have mentioned that, but two things are important. First, after antenna, you see the thing that we are seeing, the red, wonderful color, 3D pictures, those are actually called patterns. That means where the energy is directed. And the you see a term known as parameter or scattering matrix parameter. Now, these two parameters are very important whenever we go into antenna design. Now, pattern, of course, I guess we can understand that we want to know in which direction the energy is being radiated. So, a radiation pattern gives us where the energy is being radiated. Now, what is S parameter do? S parameter actually tells us how much energy is being transferred to the device or the antenna. Now, that's crucial as well. Why? Let's say you are giving watts and watts of power, kilowatts of power, but your antenna is stupid, it's inefficient. Not be able to reactance as possible. Like we do know that impedance can be divided into two things. Real part is resistance and imaginary part is reactance. Now, why do we see imaginary part? We see imaginary part, that means the energy is being stored at the antenna itself. That means we are not able to transmit the energy in the space. It is being stored at the antenna. And as an antenna engineer, we do not want that. So yeah, at the extreme right, you can see the S parameters. Academically, we want S parameters to be minus 10 dB. This is in dB scale. Minus 10 dB equates to something around 90% of power being transferred to successfully to the antenna. That means if I am giving 1 watt of power, the antenna is able to transfer 1 watt of power using minus 10 dB scale. Coming back, so we have designed the triple mode horn antenna. That is basically we have designed a source which is going to be used for monopulse. Now let's solve the next problem. It's not showing, but so next problem is the steering. Now we want to rotate our eye box instead of head. So instead of fully moving the reflector or the dish, And imagine the dish antenna at your home, you're trying to hold it up and try to move it. Instead of doing that, you're just moving a small part, action. Okay. Now, in order to do that, what we delve into was a concept of display prism. I'll not go much into the details. Just imagine this as if you have two discs and you are just trying to rotate them actually, not like in three axis. You're just trying to rotate them like you used to imagine you two hands and you are just doing, you're trying to open an eggshell or something like that, Kinder Joy egg. So something like that. You do that. You do that action, and you will see that this is how this is the action, same action or same rotation. These two pair of dielectric lenses or wedges will work. Now, why wedges? Why it is important? As you can see at the bottom left figure, whenever we direct energy, or rather if you go in optical sense, whenever we direct any electromagnetic energy, whether it's light or whether it's any microwave energy, because of the wedge nature of the dielectric lenses, the energy gets deviated in certain direction. Now, this certain direction depends on what kind of refractive index the dielectric lens has and what kind of wedge angle or slope angle the wedge has. Now, based on this, went for my animation for elevation on azimuth control is not playing. So I guess I will not be able to show you how this rotations. There was a 3D animation, like I was telling you. Imagine opening a Kinder Joy eggshell, and it was a similar kind of movement that would help while is rotated. Now, what is feature? The features is very simple. We only use a pair of dielectric wedges. Now, instead of rotating the antenna in full 3D axis, we are just rotating it axially. And even if after doing this, we are able to look or steer the beam in a conical scan. Also, this is a frequency independent. That means we can use it at any frequency, right? And we can steer both linear polarized and circular polarized incident waves. I'm pretty sure we know that lights or for that matter, any electromagnetic waves has different types of polarizations. These are LP and CP. Now, this kind of steering principle can be used for various communication and tracking application, and we decided to go forward with that. And this is the actual design that we went with. At the extreme left, you can see the same antenna or the triple mode horn that we talked about or discussed for tracking. And then on top of it, you see this yellow mark, which are the display, and equivalent. You can see right next to it. Okay. So this can be rotated to steer the beam. Now, in practical scenario, at the middle figure where you can see some gear-like structure. So, when I mean mechanical steering, what we do is we use some kind of servo motor, simple controller. We can use them to rotate these gears, and that way we can actually see the uh, where the beam is getting tilted, right? Again, on the extreme right, you can see some patterns like, again, continuing the same trend. Red means more intensity. As we go from red, green, and blue, the intensity gets lower. So again, as an antenna engineer, we try to look at whether all the energies that we have designed it for is working or not. Let's say, for example, the top one is where we design it for the sum pattern. That means it was generated at the bottommost port. A port, by port I mean the energy you can see is getting from the bottom. And as we're selecting which port we are exciting, you can see the red marks are also changing depending on that, signifying that the energy is properly distributed as we want. Now, let's also see how the performance of our antenna, how it is performing from steering. At the left, you see the same antenna with the simulated model, the actual prototype, and the gears and all. So we can see the beams, the T11 mode, it was the sum beam. So we are trying to steer it from top to bottom. You can see, yeah, the beam is slightly moving from top for beam 1, 2, 3, 4, 5, and you can see it's coming from top to bottom. And the same thing we can see for the other difference mode. Here also you can, also you can see that this mode has most of the or the desired direction, and the two difference beams have like blue color and the desired direction. That means we want the least color, least energy to be transmitted in that direction. And see that this model works perfectly fine, and we are able to direct all the energies in desired direction. Now, we have satisfied the first two conditions, or rather the second and third conditions, where we are able to move our eyeballs, or rather we are able to achieve the beam steering. Then we are able to also generate molecular tracking. But one component that was the gain, that how are we going to achieve gain? We didn't achieve that yet. So for that, a common solution that engineers use, actual engineers use, is reflectors. So here you can see what is a reflector. That's a big reflector similar to the dish antenna. That's basically a reflector. So it just redirects the energy that's coming out from the source with much more concentrated gain. So that's in the game. On the extreme right, again, you can see some of the current distribution on the reflector. Again, the same terminology. Red means more power, most power, and as we turn to the color blue, the power gets reduced. So continuing with the same terminology, we can see that for some mode or T11 mode, the energy can be along the horizontal axis of the reflector, and the other two difference mode, the energy is where energy is not. So this is the overall design that we achieved. So now coming back to the conclusion. So actually this product has been handed over to the US Navy, and they are working on the signal processing part. We're trying to whether the monopulse tracking is working, and they did a fair share of testing already. I unfortunately cannot show that. That's their secret things. They cannot we cannot share that. But yeah, this technology works, and this can be used for troposcatter communication, where we first successfully track the location where the optimum scatter volume is, and then after that we establish a connection. So coming to salient features, what are the important features? Yes, we use slip prism, so that instead of rotating, having a high, larger mechanical structure, we rotate a very smaller structure, and that as well, not a complex 3D rotation, but rather an actual rotation. Then our reflector gives us the gain that is required. Then all the other parameters for the tracking is met. Now, at the end of this, I would like to say that that's how we, as an antenna engineer, we start from the given problem, then specifications, then solving each problem or each each obstacle of the specifications part by part. Now, since we have gone through the how the past was or the present antennas, how an antenna engineer looks at a problem. Let me also try to get your interest on some of the future technologies that antennas have been used there. I think this is the first slide that I will be showing is on health diagnostics. I'm pretty sure, though it will be unfortunate, many of you might have known some relative or a friend who has got a head injury at some point of your life. I do believe strongly everyone has got to it. Now, what do you do when you have a head injury? So when you have a head injury, you will rush to a doctor and say, "Oh, I have a head injury." And what will he say? "Okay, you have a head injury. We do not know what happened. let's send you to a CT scan or an MRI, right? Now again, in India specifically, we know that CT scan and MRI are time-taking, they are pretty hectic, and some of them, specifically where you need to inject radioactive fluids so that right. Also, this CT scan and MRI, they are not available everywhere. So from that aspect, microwave imaging is an option. So this structure that you see is a microwave imaging setup. Skull cap to the skull cap. Then there are the signals coming from the antennas are being processed, and from the signals that are being processed, we are trying to locate, as you can see, using a laptop or a simple tab or a simple phone, you are able to process whether you have got any kind of internal bleeding, because that's important. Let's say, unfortunately, you get a head injury, you get an internal bleeding. You will not know at first. You might say, okay, I look fine, I can walk, I can see things. But after some time, you go to home and you say, okay, I'm having a headache, I'm nauseous, I'm vomiting. You will not know why, and there might be a lot of delays. And you know, let me tell you, every second you lose because of this clotting, this also known as hemorrhage to make the term. Because of this hemorrhage, you are losing a lot of neurons. A lot of neurons in your brain are dying. That means you will lose some physical control or you might lose that. Hence, immediate diagnostic of a hemorrhage is very essential. And like I mentioned, CT scan and MRI are golden standard, but accessing them is very difficult. So this is an alternative. That's a future study. And as you can see, the reference at the bottom, it is from October 2020 European group. They are working on this. And it is pretty new. In the last 4 or 5 years, we have developed where we are trying to look into using microwave imaging as a tool or as an alternative. Excuse me. So there's another one. It's a wearable device. It's called silent speech. Now this is also important. Now you might ask, what is silent speech? Okay, what is important? I would say as an Indian, we need it more. Sometimes you stand at a railway station, there's so much noise, you can't even hear yourself. And imagine if you have to tell some other person something that is very secret, you don't want the next person sitting next to you to know, oh, I'm telling you, okay, oh, it's secret. Next person hears it, okay, he dials, he puts it before you, you're gone. So yeah, so this technology is being developed. Again, you can say this is 2022, it's very recent, in the last couple of years. Like the first, I don't know if you remember, many of us, I believe, have also read biology, aspiring to become doctors. But the sound that is produced in our mouth is due to different muscle movement. It's like, I think in literature also they used to tell us there are some nasal movements. If your tongue touches your upper nasal cavity, you produces that sound like something like that. Then you have something like your tongue has to touch your teeth. If it doesn't touch your teeth, you cannot spell those words or spell those alphabets. Similarly, it has to go and touch the back of the tongue. So, from an animal engine, this is very important or very interesting. Actually. It is similar to tracking, isn't it? Right? We're tracking the movement of the muscle. So, if we can somehow track it, if we know at which frequency or which energy this can be tracked, we can certainly see or understand what a person is saying within a signal, like actual voice. In just moving the muscles. Right now, I can also say if some of you are thinking within your mind, actually you are having a muscle movement. So if I have the headset, I can listen to you again. Yeah, yeah, I get you. So yeah, and there is a very interesting. I think someone in the someone from MIT, they have developed something else. It's not related to this. They have developed something based on ultrasound, and he connected it to Google or internet. So he wears a big old headset similar to what we are seeing in the middle. So he sits in front of an interviewer from it's a mock interview, it's like a stage interview. the interviewer asks him tough questions. Let's say you are faculty, you are asking just a tough question, and he is having the headset. He's not saying anything, but he has muscle movements which are telling the internet, find this. And the internet itself is telling him in the ear, okay, this is the answer. Then after hearing the answer, he's telling an answer. So yeah, that's a very cheat code that can be done. So this is another interesting, and I think it has a lot of applications, and people are going for it. So there are different colleges or different technologies. Like you have circuit engineers who can build the circuits. We have signal processing. Right, your speech processing is very difficult. You need to understand how each vowels work. We need a speech engineer. And then, of course, from an antenna engineering point of view, antenna is also important. So yes, this is another interesting thing, and I'm very interested with this. Next, of course, there are some more. Yeah, this is also a future, and they have been present, and they are still there. Like I think everyone of us has learned about Starlink, like the future of communication, the future of we are our lead to the satellite, and we're gonna get the internet, the bandwidth we want. Yes, we're gonna watch some movie at very high speed. Yes, we're gonna do it. We're not gonna wait for the buffering and all. Yes. So Starlink is planning to do that. What Starlink is doing that is using a bunch of or a sequence of satellites, which are also known as CubeSats. Now let me tell you CubeSats. What is CubeSat? CubeSat is basically a bunch of unit cells. Now, how we can define this unit cell is that if you pay attention to the extreme right of the screen, you have like a frame-like structure. This is a frame of an actual satellite. So this is called 3U, 3-unit cell of a satellite. Now, 3 unit cell satellite, why? Because from visually you can differentiate that, okay, there are 3 stories. Okay, I understand that there are 3 units and 3 stories. Now, what is the reason and why it is unit is because each unit has a dimension of 10 centimeter by 10 centimeter by 10 centimeter. That equals to 1000 centimeter. So that is 1 unit cell. Okay. So whenever someone asks CubeSats, the CubeSats are built of different units, and 1 unit is 1000 centimeter cubes. And you can see that the middle there's few antennas, some phase arrays, some patch antennas, different kind of antennas that can be attached to this CubeSats, and as well as along with that, you can see some kind of protrusion. These protrusions are for solar panels. Of course, if you do not in space, we cannot have wires, we cannot have anything. The only source of energy is sun, so we need to have solar panels. This is another interesting. I'll say like it's not future, it's also present, but I think more work needs to be done in this regard as well. The next is it's already in development, but I'll still say it's a future because yes, I am pretty sure everyone's heard about Tesla, and I guess to some extent Volvo as well. I would really encourage you guys to go through Tesla, maybe online go through a Tesla, how a Tesla brand works. Like, it's pretty amazing. Teslas don't make sound. I feel like, bro, make some sound. I'm not hearing anything. What's the engine sound? I've been hearing engine sound for so long. My 20 years, my 25 years since I have several cars. I'm used to it. The silence is different. Why? Because it's running on batteries, right? It's basically an. Someone actually said that, but I don't think Elon Musk is gonna like it. It's it's like an edition, but and very good edition. Where you if you see it with privilege and you like it, so like that. Now, that from an engineering point of view, you know, Tesla. I had the fortune of sitting in a Tesla. What you can do is you can just leave the steering and let it drive. It will locate, okay, it will drive the cars right next to you, left and right. You look at the people standing in front of you and it will drive by itself. How is it able to do that? Definitely it's tracking, right? Now if it's tracking, okay, you might call it sensors, but as an antenna engineer, I'll call it antennas, bro. It's antenna and they are tracking, right? So, of course, you can see a front panel here, CAD models of antenna, so front of a car where antennas will fit it, and which is trying to track objects in front of it. Along with that, we also have some kind of antennas which are fitted at the sideways of the car. Of course, some of us are very bad drivers who might bump into some people or some other cars that are moving sideways along with us. So these antennas help us assist that no, you do not bump into other people, right? And then there is also a very interesting feature. This I like the most. That's the parking assist rear collision. We do have an issue. We find it so hard to drive our car backwards, right? It will be so good if we have an assistant. But we usually have our brothers or someone of our relatives from our house. Okay, can you just stand in the back and tell me if it's hitting the wall or not? So that's being done by antenna. So it will be saying, okay, you are here, 10 centimeter, it will start beeping, it will sense and it will start beeping. So yes, these things are also done in antennas. So I would say in total, antennas are really interesting. Sometimes we fail to appreciate how much our life has changed because of antennas. Some people might call it sensors. It's sensors, but antennas. How much it has changed our life from communication to tracking to defense. If you wanna be ahead of our enemies, we need to be technologically advanced. And how can you technologically advance? If you have good communication. If you are not able to tell your superiors, oh, we are being attacked, think about it. It will become like old ages, right? When you are sending a person, go run and tell. You will be running or you will be driving, let's say. Nowadays, driving and telling. That's very late. By that time, country is gone. Yeah. Certain jamming things, like I mentioned. I don't know. This might be a little political, but nuclear war is like threat of nuclear war is right. People are very much afraid. So from that aspect as well, from defense, we need to know like, do we have an Israel kind of and where if some missiles track that and destroyed in the air before reaching the on land. So those kind of thoughts and how that works, a major part, a major thing that works for that assignment. So I would say this are important, and of course, yeah, there are cool things like cars, smartwatch, which can track your health. Okay, with that, I think I would like to end my talk. If you have any questions, feel free to ask. I'm a very passionate person, specifically in last 4 or 5 years working with antennas and different things. I'm like passionate. Any imagination you can ask, I'm ready to answer. We can go beyond. Yeah, I can go. Oh yes, yes. It's a very good question. Another thing we need to understand when we say beam steering and button matrix actually comes in the category of beam switching. So beam switching is where we have a fixed beam direction. Okay. So let's again coming back to my favorite example. I always give this example. Our human head. Now let's say I'm doing beam switching. That means I have only 4 positions. I cannot move my head continuously. I have this. From this, I'll just do this. I can do this. Or that is so Butler matrix or some kind of green lenses. These are called beam switching networks. So they actually switch the beam in certain direction. Now, certainly in applications like base stations that I was mentioning, where you just need to switch in certain directions, beam switching is a very cost-efficient technology. And, but then if you want to scan all over the place and you want to have a complete as well. That can be achieved only electronically or rather some kind of information.
So we are almost about to done. If the participants who are in online mode are having any query or any question regarding the session, you can ask. So I'm repeating again. If any one of you having any query or any question regarding the session, please unmute yourself and raise your voice. Okay, so we are concluding. Thank you.
Yeah, so we went through the session, right? Thanks for inviting me here. It was really nice.